Okay, we are now recording. Okay, welcome to the physics class for April 27th. First off, before we start, anybody have any questions about anything at all, aims or rumors that you've heard or anything? Okay, nothing, all right. Hope everybody had a good weekend. No homework, it was a beautiful weekend. I hope you got outside. I realize you can't go join your friends and have big parties, but it's beautiful outside. I hope you got outside and just walked around, enjoyed the incredible weather. Good, I'm glad to see that some of you did. Okay, so let's talk a little bit about the test. Now on my side, the test worked out way better this time than it did the first time. The Canvas is really good at doing multiple choice tests. So that first part of the test where it was all multiple choice, okay, as far as from my point of view, everything really well. I did have one student, only one, who reported to me that she wasn't able to see the pictures that accompanied a lot of the questions, but that when she got out her phone and she accessed Canvas via the phone, then the picture showed up okay on her phone. It was just her computer that they didn't show up on. So I'm guessing that her computer doesn't have all the viewers. Oh, okay, so Yasna had the same problem. Okay, so it wasn't, how many of you experienced that problem? So right now I've got 2 people who had it. Nobody else popped up? Nobody else wants to say anything? Okay, so Yasin, did you do the same thing that the other student did? Did you get on your phone? Okay, and so when you looked at it on your phone, it was fine, but your computer didn't. Okay, I don't know what to tell you. The whatever picture viewer is built into your browser apparently couldn't handle it. Yasin, what browser were you using? And Annie, you were the other one. Okay, so Yasin was using Safari. Let's see, is Annie even online here? Okay, so Annie was using Safari too. I think we may have a trend here. Okay, so all I can suggest then is the next time we take the test, see if you can use a different browser other than Safari. That seems to be the problem. Okay, so anyway, the first part went really well. In fact, a lot of people got perfect scores on the first part. And now the second part, that's where you did the work on paper, at least most of you did, and then uploaded the photographs. That seemed to go really well. It was grading, it was good. We didn't have those weird glitches with Canvas like we did last time. So next time we take our last exam, we've only got one more exam before school's over. I'm going to do it the same way. Okay, so I see that Annie's Chrome is messed up. Well, you're going to have to get it unmessed somehow. Joseph is saying that he used Safari and he didn't have any problem. So don't know what to tell you. So maybe a good thing to do then is when we take the next test, in addition to your computer, have your phone sitting by so that if the pictures don't show up, then you can view it on the phone. Hopefully it'll work well there. Okay, so most of the scores were really good. Most of you either got A's or B's. A few of you didn't. But most everybody got A's or B's. So maybe I should make my test harder next time, huh? Okay, well, so I don't intend to talk more about the test, and also I don't intend to have you to redo all the problems that you missed. It's just when you got that many multiple choice questions, it really just doesn't make sense. So we're not going to talk anymore about the test unless you have some specific questions, and even if you do have some specific questions about the test, let me ask you to hold them until we get to the end of today's class session, because we got a whole bunch of really important stuff that we need to get through. So let's go into that. And then at the end, if you have questions, remind me and we'll talk about them then. Okay, so we're going to start into chapter 27 today. With quantum theory, which is also known as quantum mechanics. This is my favorite part of the year. I love all of the mind-blowing stuff that we're going to go over, and this is a real shame that we're doing it online, because one thing that I really enjoy is watching students' minds explode, as we talk about all this weird stuff. And I can't see your faces, so I can't see your brains exploding. What a disappointment. Okay, so when you read the chapter tonight before you do the homework, because I know you always read the chapter before you do the homework, they're gonna talk about two very important problems, two very important mysteries that perplexed people who were working with light. So let's just take a minute and review. So way back in ancient history, starting with Aristotle, people assumed that light was a little particle. And Aristotle especially, he really harped heavily on this. He thought that light was little particles so you got a light bulb and it shoots out little particles and they bounce off whatever thing, they come back into your eye. And for many, many, many years, everybody just assumed, yep, that's it. And then along came Thomas Young, who proved that light is not a particle, it's actually a wave. And so we've talked a lot about that. I don't think I need to go into that in any more detail. So from that point on, everybody says, okay, light's a wave. And so everybody was happy. The wave theory of light explained all of the phenomenon that they had encountered, until these two things came along that didn't fit with the theory. Okay, so one of them is radiation from incandescent light bulbs. So basically, the people who made light bulbs, they wanted to understand the physics of why light bulbs gave off light. Because the more you know about the fundamental physics, the better you will be at making light bulbs that people want to buy. So what they did was they did some experiments where they took the filament that's in the light bulb and they heated it to different temperatures to see what happened. And then they measured the radiation as a function of frequency. So let's look at the lower curve here. So we got this 4,000 Kelvin. So that means that they heated the filament to a temperature of 4,000 degrees Kelvin. Okay, and then they found out, and so at all the different frequencies, they measured the light, and they found out that they got the maximum amount of light at about 2.5 times 10 to the 14th hertz. But all of that light, well, light isn't really the right word to use for it because it was all infrared. So if the human eye can't see it, light is not the word that we use for it. So the radiation, the electromagnetic radiation that was given off, was almost all down in the infrared range. So you touch the wire and you can see it's hot, but you don't really see it glowing. The visible light is over here. It just gave off a very, very faint glow. So when they heated up to 5,800 degrees Kelvin, okay, now we're starting to get a lot of visible light. Okay, but even then, the majority of the light was still in the infrared. And then here's the curve for 8,000 Kelvin. So they measured these curves experimentally. But then they said, okay, we think that that why the light is being given off is because the electrons, when you heat them up, they vibrate really fast. And so based on that theory for why light is being given off, they came up with some curves for what they thought the curves should look like based on their understanding of the theory. And the theoretical curves did not match with the actual measured curves. Okay, so clearly they didn't understand the theory well enough. So for many years, they scratched their heads and said, man, why does the curve from theory not match the curve that we get from reality? That was a big problem. And so there's the light bulb problem, if you want to call it that. Okay, but that was only one of the problems that perplexed scientists for a long time. The other problem is the photoelectric problem. Okay, so what you see here is a photocell. In fact, let me clean it up so get rid of all the stuff that might potentially confuse you. All right, so this is a solar panel, a solar cell. They've been around for a long time. So if you were to take a parallel plate capacitor like the kind that we've been talking about many times for our electron guns, okay? So what you've got in here is basically a parallel plate capacitor, except some of you are going to say, hey, wait a minute, those plates are not parallel, those plates are curved. Yeah, okay. They don't have to be parallel. It's okay for them to be curved. Now, if they're curved, that makes the mathematics a little bit more difficult, but it actually makes them so they work more efficiently. So if you know something about calculus, which many of you do, and hopefully before next year's over, a lot of you will, if you're good at calculus, you can still do the math, even though it's not a parallel plate. But I'm not going to worry about the math. Let's just say we've got this capacitor, and it's been known for many, many years that if you make your parallel plate out of certain types of metal, when you shine light on them, they will give off electrons. Just the act of shining light on the metal causes it to give off electrons. Now, it can't be just any old metal. You know, iron and copper and things like that, it doesn't work so well for them. But if you get other types of specialty metals, when you shine light on them, they give off electrons. And so if you were to hook it up in a circuit like this and hook up a little meter there to measure how much current is flowing, what you'll find is that you actually do get current flowing through this circuit, and the light is what's causing the electrons to jump across and causing the voltage to build up. Okay, so far so good, no problem yet. Okay, so let's take it to the next level. You need to understand some basic physics to understand why there's a problem here. Okay, so what scientists did was they said, well, we know all about parallel plate capacitors, and you guys in the test that you took on Friday, you proved to me that the majority of you also know about parallel plate capacitors. There's a few of you who are a little shaky on it, but you guys know that if instead of using this as a photocell, if we used it as a parallel plate capacitor where we hook it up to a battery, okay, the energy that we would give the electrons, which is Q times delta V, you know, that's the kinetic energy, okay? It follows this equation right here, okay, if we were using it as an electron gun. So what scientists said is, let's do it as an electron gun in reverse. So what they're doing is, instead of using a battery to excite the electrons, they're going to use light to excite the electrons, and they're going to use the battery to stop the electrons, okay? So up until now, we've always used the battery to cause the electrons to shoot across. Now, we're going to use the battery to stop the electrons, because when the light hits them, the light wants them, they can shoot across. And so what we're going to do is we're going to take a battery, a special kind of a battery that has a little knob on it, so we can adjust the voltage. So this schematic down here, just think of it as a battery with a little knob on it so you can adjust the voltage. Okay, and so what scientists found was that there's a certain voltage where if you get it just right, you'll be able to stop the electrons from getting across. If you're a little bit less than that, if the voltage is a little less than that, then you might stop some of the electrons, but others of them will still get across. And then once you get above that threshold, then you can go, then it doesn't really matter because you've stopped all the electrons. So scientists did a bunch of experiments where they found out how much voltage was necessary to stop the electrons from getting across. Okay, and they called the voltage that it did this, they called it the stopping potential. Because hopefully you guys remember when we first talked about voltage, when we first introduced the idea of what is voltage, the book referred to it not as voltage, but they referred to it as electric potential. So potential is basically another word for voltage. Electric potential is voltage. So in your book, when you read the book tonight and they talk about the stopping potential, what they really mean is the stopping voltage. Okay, so the stopping voltage here is very important, because if you take that voltage and you multiply it by the charge of an electron, what you have just done is you have measured the kinetic energy of those electrons. And that's the reason the scientists did this. They wanted to know how much energy did these electrons have that they got from the light. Okay, because what they really wanted to do is they really wanted to measure what is the energy of the light. That was what they were ultimately after. Okay, so they figure the light comes along and the light gives its energy to the electrons. So if we can measure the energy of the electrons, what we're doing is we're measuring the energy of the light. And this equation that you see up here, Q delta V, that tells us what the energy of the electrons is. So if we measure delta V and we know Q, bingo, we've just measured the energy. All right, so that's what they did. Okay, so far, no problem yet. Okay, Um, all right, so uh, so now scientists did two kinds of experiments. Okay, the first kind of experiment was they changed the frequency of the light that they were shining on the metal in order to see how that affected the energy that the electrons had when they got excited by the light. Okay, so they started off with red light. So red light is relatively lower frequency compared to green and blue. Okay, and so they shined red light on the metal, and then they adjusted the voltage until they got it to where they just barely stopped the electrons from coming across. So they measured what was the stopping potential for red light, and they calculated from that what the energy of the electrons was. And then they switched from red light to green light. Green light has a higher frequency, and they expected that the higher frequency would show up in terms of the electrons having a higher energy, and it did. Okay, everything worked exactly as they expected. When they went to a different color of light that had a higher frequency, then yes, the electrons did in fact have more energy. And then when they went to blue light, which was even higher still, then yes, as expected, it took a higher stopping voltage in order to prevent the electrons from hitting there. So everything worked out fine. So no surprises. Increasing the frequency of the light did in fact increase the frequency of the electrons, which means that the higher frequency light has more energy than a low frequency light. So everything's cool here, no surprises yet. Now here's where it gets interesting. Okay, so what they did next was they said, okay, let's just pick one color and let's stick with this one color. So red, green, I don't care, you pick a color. Let's say it's red. Okay, so then what they did was they said, okay, so we'll do an experiment where we have the brightness at a certain level. And then what we'll do is we'll crank up the brightness of the light. We'll keep the color the same. We'll just increase the intensity of the light. So they started off with a really dim red light. They measured the voltage. And then they went to a much brighter red light. And they expected that the electrons would have more energy because brighter light has more energy, right? Duh, right? So they were certain that when they went to a brighter red light, then the electrons would have more energy. The stopping potential would be different than it would with the dim light. But that wasn't what happened. What they found out was that no matter how bright they made that light, the stopping potential was the same. Now, it is true that they did get more electrons, okay? So when they go to a brighter light, they did get more electrons, but the energy of the electrons did not change. And that's what the stopping potential tells you. The stopping potential tells you what was the energy of the electrons. So this was a huge problem, okay? Because according to everybody's understanding about how light, or about how waves work, okay, increasing the amplitude of the wave should have increased the energy of the electrons, but it didn't. So this was a big, big problem, okay? And it was called the photoelectric problem. And for a lot of people scratched their head for many, many years about this. And then the other problem that I talked about earlier, the light bulb problem. Okay, so that one also. So we got these two problems. People scratched their heads for a long time about this. Now, I want you guys to fully understand why this is a problem. So here's an example that hopefully will help drive it home. Okay, so what you see here is a picture of a wave hitting a wall in a marina here. So I want you guys to assume that you are Poseidon, or maybe you're Neptune, depending on whether you're Greek or Roman. Can somebody type in, who is Poseidon, or Neptune, depending if you're Roman? Uh, you guys know about Greek mythology. Okay, the god of the sea, excellent. Okay, so let's suppose that you are Poseidon. And you took, when you were younger, when you were a teenager, you took Mr. Hendrix's physics class, okay? Now you're all grown up, you're an adult now, but you took Mr. Hendrix's physics class when you were a teenager, and you did not get an A, you only got a B, and you're really mad about it, okay? So you want to get even with Mr. Hendrix for giving you a lower grade than you think you deserved. All right, so you guys know Mr. Hendrix is really into sailing, obviously. All right, so let's suppose that I'm out sailing one day and I want to eat lunch, And so this is a little marina, and there's a restaurant, say, right over here. And so I want to park my boat here so I can go and eat lunch. Now, obviously, I'm not going to park my boat at the marina if there's waves like this. I mean, that would be stupid. I may be dumb, but I'm not stupid. So let's suppose that it's a calm day. So you're not getting big waves like this. So here I come along in my boat. I park my boat right here. I tie it up to the dock. I get off. I go into the restaurant. I eat lunch. And remember, you're mad at me because I gave you a B instead of an A. And you are Poseidon. So you say, now's my chance to finally get even with Mr. Hendricks. What I'm going to do is I'm going to destroy his boat. I'm going to use the power of the sea to smash Mr. Hendricks's boat into pieces. Okay, so sound like a good thing to do? All right, so hopefully you realize there are two ways that you could do that, okay? So with classical waves, which, like ocean waves and sound waves and the kind of waves that people are used to, there are two ways that you can increase the amount of energy that these waves are delivering to whatever they're hitting. Because remember, my boat is parked right here. And so as Poseidon, it's your goal is to make the waves destroy my boat. So two ways you could do that. One is you could increase the frequency of the wave, because every time a wave hits the boat, the boat's going to hit against the dock. And so if you increase the frequency, that means the boat is going to hit the dock more often. And so that would increase the probability of destroying my boat. But another way is the amplitude of the wave. So what you see right here, this wave that just hit the dock here, that was a wave that had a huge amplitude. These are big waves. Okay, so if you're Poseidon and you want to deliver a lot of energy to my boat in order to destroy my boat, there's two ways you could do it. One is you could increase the frequency. The other is you can increase the amplitude. That's the way classical waves work. Well, what we just talked about with the photoelectric effect, we find out that one of those ways worked, but the other way didn't. Increasing the frequency of the light waves did in fact increase the energy of the electrons, so that was cool. But increasing the amplitude had no effect whatsoever on the energy that these electrons have. And it should have, okay? That's the way classical waves work. Okay, so you understand now the magnitude, or you understand now why it is a problem, why this photoelectric problem really is a problem. There's something going on here that we don't fully understand. Okay, all right, well, a lot of people spend a lot of time thinking about this problem. And in fact, one guy in particular, he wasn't even a professional physicist. He worked in a patent office. He was a patent clerk working in an office, and he just was kind of an amateur physics. He dabbled it in the evenings in his spare time. So he spent a lot of time thinking about this problem. Anybody want to take a guess as to who this patent clerk is? Would it help you? Okay, yes, okay, Hiram, you got it. So Einstein, that's the guy. So Einstein, in his spare time, whoops, okay. So in his spare time in the evening, he says to himself, okay, so light clearly is not behaving the way that waves should behave. So, it's not behaving like a classical wave. So maybe it's not a classical wave. Well, what does that mean? Maybe it's a quantized wave. Okay, so we've already talked about this before, and I've already spilled the beans here. I've already told you, but I mean, pretend that we didn't know that. Pretend that in the pre-Einstein days, when everybody thinks that light is a wave, they're thinking that light is this kind of a wave up here. It's a continuous wave, like the waves in the ocean, or like a sound wave. Okay, so after Thomas Young proved that light was a wave, everybody says, okay, but they thought it was this kind of a wave. So Einstein was the first person to propose that maybe it's not that kind of a wave. Maybe it's actually this kind of a wave. Maybe it's a little wave packet, okay? And so then they says, okay, so this is a slide that you guys have seen before. Several classes back, we talked about this. And so Einstein was the first one to actually figure this out. He said that maybe what's happening when light is given off is that the electron is, which is up at the higher level here because it's been bumped or somehow it's been excited at the higher level. So it's jumping down from here down to here and is giving off light, but it's not giving off this kind of a light. It's giving off this kind of a little blip here, okay? And so then when you have a light bulb, what's really happening is not this, but actually it's this, okay? Einstein was the first guy to propose that. And once he did that, then all of a sudden, both the photoelectric problem and the other problem that I talked about, the light bulb problem, all of a sudden things started falling into place to where they made sense, okay? So think of it this way. Let's go to the photoelectric problem because I think that's the one that's easier to understand. Okay, so here's a piece of metal and it's got a bunch, these little circles there, that's supposed to be an electron. This is the best I could do it, representing electrons. Okay, so we got all these electrons in the middle there. Along comes a photon. The photon hits the electron, and the electron absorbs the energy, and with all that extra energy, it now comes shooting out of the metal. But here's the thing, the electron can only absorb one photon. So when you increase the amplitude of the light, you're not increasing the energy of a photon. All you're doing is you're increasing the number of photons, okay? But each individual photon, it has a certain amount of energy, and that's all it can have. So when you crank up the brightness, you're not changing the energy of the photons, you're just changing the number of the photons. I hope this makes sense. Okay, so each one of these photons that got ejected out here, they got ejected because they absorbed one photon. And so this all of a sudden explains the photoelectric effect. This explains why it is that that when you crank up the frequency, then yes, the electrons have more energy, but when you crank up the brightness, the electrons don't have more energy. You do get more electrons, but each electron has the same amount of energy. So Einstein was the first one to explain that. And that is the reason that Einstein got his Nobel Prize. A lot of people think that Einstein got his Nobel Prize for coming up with E equals mc squared, but he didn't. It turns out that E equals mc squared is actually not that hard to come up with. And in fact, that's my plan for Wednesday. On Wednesday, we're going to talk about that. Okay, so it was the photoelectric effect that got him his Nobel Prize. Okay, all right, so let's do some more with the photoelectric effect. So what we're doing here is we have plotted the kinetic energy that an electron has as a function of frequency of the incoming light. Okay, so we start with red light and we get relatively low frequency. Go to green, we get we get relatively low energy. Go to green, we get more energy. To go to blue, we get more energy. When you go to ultraviolet, that's when you really start getting a lot of energy. Okay, so this is the curve that you get if you measure the energy of the electrons as a function of the frequency of the light. Now, what you see here is what you get for one particular metal. If you switch it out for a different type of metal, what you find is that you get curves that are slightly displaced from each other. Metal B here, it doesn't give off as much energy. I mean, if you hit it with blue light, okay, let's say you shine blue light here. So metal A, the electrons have a lot of energy. Metal B, the electrons, they come out, they got energy, but not as much. But if you shine it on metal C, you don't get any electrons out at all, okay? All right, but the really interesting thing here is that the slope of all these lines is exactly the same. And that's super important, okay? It didn't matter what metal they looked at. When they did the experiment, they found that the slope was always the same. Now the y-intercept is different, but the slope was not. Okay, so if the slope is the same, tell you what, let's do. Okay, let's look at, so we know that the energy of the electrons is proportional to the frequency. Now you guys know what's coming next, I hope, right? I don't like proportional signs, I like equal signs. So what do I have to do if I change that proportional sign to an equal sign? What do I have to do? Somebody type it into the comment box there. Add a constant, exactly right. Okay, so that's what I'm gonna do. Okay, so I've added a constant. Now, normally when I add a constant, I call it K. But in this case, Because these curves here, they don't start at 0, they start somewhere down here. So what I'm going to do is I'm going to put it into y equals mx plus b form. So the constant here, I'm going to call that m, because that's the slope of the line. And then I do have to put in a b here because you see they don't start at 0, they start somewhere below 0. And I put in a minus b just to drive home the fact that they start off below 0. Okay, so this is the equation that I'm going to use. So the energy of the electron is equal to some constant times the frequency minus some offset, and that offset changes depending on what the metal is. Okay, so now I want to know what the value of that constant is. So I'm going to just have to perform a bunch of experiments. And so we have the data right here. The value of that constant is just going to be the slope of this line. Okay. Now over here on the y-axis, the energy is not given in joules; it's given in some other unit that we're going to talk about in just a few minutes. So if I were to change the unit here so that my y-axis is joules, then the slope of this line, if I were to calculate numerically what it works out to be, it turns out to be 6.63 times 10 to the negative 34. And it doesn't matter what metal I'm using, it's always going to be the same. 6.63 times 10 to the negative 34. Where have you seen that number before? Ah, very good. Jaron recognizes it. Yes, that's a number that Coach Miller has been talking about in your chemistry class. Okay, that is H. Okay, it's called Planck's constant. Actually, Planck is probably a better way to pronounce it, closer to the correct way. So Planck's constant, yes, this is where Planck's constant came from. Okay, so because it's such an important number, we're going to give it its own letter here. We're going to call it H. Okay, so the energy of the electron then is going to equal Planck's constant times the frequency of the incoming light minus some offset, and that offset, it changes depending on the metal. Okay, all right, so this is where Planck's constant comes from. Now let's talk about that offset. Okay, so let's say that we've got metal A here. This frequency that you see right here, this is called the threshold frequency. If the frequency of the light is anything less than this amount here, you don't get any electrons out. Okay, so if you start off at this frequency, you get nothing. Increase the frequency, nothing. Still nothing. Only at this point do you start getting electrons out. But if you were right here at 4.5 times 10 to the 14th hertz, the electrons that you get out would just barely make it out. They would have zero energy. They would escape from the metal okay, but then they wouldn't have any energy, so they just kind of sit there. So if you want them to actually have some energy after they come out, then you have to go up above 4.5. So for metal B, you can see the threshold frequency is a little bit higher. And for metal C, it's higher still. So this threshold frequency, this is a measure of, it's an indicator for how much energy you need in order to break the electrons free from the metal. So you guys know from your chemistry class, you know about something called the electron cloud. Okay, so inside metals, electrons are not very tightly held. And in fact, they can kind of roam around at will inside the metal. And so we say that all of the metal atoms, they share the electrons in what's called an electron cloud. So if we want to kick the electrons out of the metal, well, it takes some energy to break it free. Okay, so we're going to call that the work function. All right, so if we take Planck's constant times whatever the threshold frequency is for whatever metal we're interested in, that number will tell us how much energy is necessary to break the electron free. And we have a special name for that. We call that the work function. So make note of this because it's going to come in very handy in tonight's homework. All right, so what we have now is the equation that relates everything all together. So the energy of the electron is equal to the energy of the incoming photon, which is given by HF, minus this B value, which is called the work function. Okay, so the photon actually is going to have more energy than the electron. Okay, so let's say you got a photon that's coming in with 10 whatever units you want to use for energy. Okay, let's keep it really simple. Okay, let's say it's got 10 energy units, the photon coming in. Okay, so the photon comes in, it hits the electron, okay, and the electron jumps out, but some of those 10 units of energy got used up in breaking free. So let's say that three units of energy, that's what it caused to break the electron free. So that means once it gets out of the metal, it now has 7 units of energy left over. Okay, so remember this equation right here. The energy the electron have is going to equal the energy that the photon had, which is given by HF, minus whatever the work function of the electron is. Okay. All right. So, okay, so this is just a page that kind of summarizes everything that we just said. So now we know what the energy of a photon is. The energy of the photon is Planck's constant times whatever the frequency of the photon is. Okay, the energy that's needed to break an electron free from the metal, which is what we call the work function, that's equal to Planck's constant times whatever the threshold frequency is for that particular metal, and that's different for different metals. Okay. Oops. Wait a minute. There's. Oh, okay. All right. Yeah. Sorry. Okay. Yeah. So that threshold frequency is different for the different metals. Okay. And then last one is the energy that's left over with the electron is just the difference between the two. However much energy the photon initially had minus whatever the work function was, that's how much energy the electron has left over. Okay, so when Einstein figured all this out, it explained it explained the photoelectric problem, and it also ended up explaining the light bulb problem. Now, it's not my intention to talk about the light bulb problem in today's lecture. I'm going to let you guys read that for yourselves. And by the way, I don't expect you to fully understand the light bulb problem because the light bulb problem is a little bit more subtle. The book doesn't even fully explain the light bulb problem. They talk about it, but they don't really explain it. And so I'm not going to try either. I just want you to recognize that there is a thing called the light bulb problem. And when you get into university level physics, then you'll be able to understand that one a little bit better. But here at the high school level, high school physics is all you need in order to understand the photoelectric problem. It's a lot simpler problem. Okay, so let's do a couple of problems like you will see in tonight's homework. So let's suppose that one of your homework problems says, how much energy does a blue photon have? And they're going to have to tell you the wavelength because, you know, there's different shades of blue. Remember the lasers that we worked with? We called them blue lasers, but they weren't really blue. They were really more purple. Yeah, and their wavelength was like around 410. Okay, so let's say that we go to something that actually is blue, and that's 440 nanometers. Okay, so I want to know, or at least the guy who wrote your homework problems, he might want to know, or maybe the gal who wrote them, might want to know what is the energy of a blue photon. So anybody want to tell me what is the equation that we would use to figure out what's the energy of a blue photon? If only we had an equation that related energy to some other things. Okay, E equals HF. Very good. Thank you, Cohen. Yes. Okay, E equals HF. That's the equation. Except they didn't tell us what the frequency of the photon was. They told us the wavelength. So then we say, oh, if only there was an equation that related wavelength and frequency. Well, yep, there is. Okay, we know that the frequency is equal to C over lambda. Okay, so now we know that the energy, we could express it as HF, or if we want, we could have expressed it as HC over lambda. All right, so we know H, that's Planck's constant. We know C, that's the speed of light. They told us what the wavelength of the light is, so pretty simple there. Now it's just plug and chug. Okay, sorry about the 10 to the 34 there. That shouldn't have come out like that. Let me fix that real quick. Nope, that wasn't the one I wanted, sorry. This is the one I wanted. Okay. Okay. There, does that look a little better now? Okay. Come on. Okay, there, it looks a little better there. Okay, so all we have to do is just plug and chug. There's Planck's constant, speed of light, the wavelength of light, and so the answer works out to be 4.52 times 10 to the negative 19 joules. Pretty straightforward. I hope you agree that if all your homework problems are like that, then it's going to be pretty easy. Ah, okay, sig figs, very good, thank you. Yes. Are you going to count that as a wig point? Oh, you probably are. Okay, but that's only one, so I'm allowed two more. Okay, so one wig point because I didn't follow my sig figs rules. Thank you, Yazin. Okay, so now here's another question like you might see in tonight's homework. So we just got through calculating that a blue photon has 4.5 times 10 to the negative 19 joules of energy. What voltage would I have to use in my electron gun if I wanted to shoot an electron that had the same amount of energy as that blue photon? Okay. Anybody want to suggest a way to approach that? What voltage? Now, there's several steps here, so I don't expect you to get it all. In fact, tell you what, how are we doing for time? Yeah, tell you what, rather than making you guys figure it out, I'll be nice to you today. Okay, so let's go through exactly the way that we would if this was last Friday's test. Okay, we know that the definition of voltage is work divided by charge. Okay, and we know that however much work we do on the photon, on the electron, that's how much energy it's going to have. So if this is the amount of energy that we want it to have, and we know that it's an electron, so we know what the charge of an electron is. So all we have to do is take this number, divide by the charge of the electron, and bingo, that'll tell us, okay? So it works out that if we have an electron gun where we power it with a battery that's 2.8 volts, that electron is going to have the same amount of energy that that blue photon would have. You guys agree that that's pretty simple? Okay. Too simple, right? We need something more fun than that. Okay, so let's take it to the next level. Okay, let's suppose that I got a blue photon, which we know we just got through calculating how much energy it has. Okay, and let's say that this blue photon is going to hit this parallel plate capacitor. And so however much energy the photon had, let's suppose for a minute that the work function of this metal is 0. Let's suppose for a minute that all of the energy of the electron is equal to the energy of the photon. So the photon has a certain amount of energy. It gave 100% of its energy to the electron. We didn't have to use up energy to get it broken free. Okay, so when these electrons come shooting out of here, they have the same amount of energy that the blue photon did, which we just got through calculating was the same amount of energy that it would have if it came out of an electron gun that was powered by a 2.8 volt battery. Okay, so these guys come shooting out with energy. So what we want to do is we are going to take our electron gun and we're going to use it not as an electron accelerator, but we're going to use it as an electron stopper. So we're going to take the battery and we're going to switch the battery around so that we put the negative charges up here. So and the positive down here. So when these guys come shooting out of here with this much energy, they come up here, but they get repelled, and so they don't make it. Okay. Okay. So you guys agree that if the work function was 0, if the electron or if the photon gave 100% of its energy to the electron, then 2.8 volts would be the right amount of voltage to just barely stop these guys so that they don't make it to the other side. Does that make sense? I'm worried that I'm going a little too fast here, so I need a couple either thumbs up or thumbs down or some sideways. Okay, so one person says he thinks he understands. How about the rest of you? Okay, all right. Okay. One or two more. Okay, so we got one yes and one maybe. Let's have a couple more input. Okay, all right. So it looks like most of you are saying it's okay, and those of you that aren't quite getting it, well, if you can think of a question to ask, go ahead. And if you can't, then okay. So why is it enough to stop it? Okay. So the answer to your question, Darren, is because if this was an electron gun, okay, so forget forget the photons. Let's suppose that we're going to use this as an electron gun. So we just got through calculating that 2.8 volts on our electron gun was the right number to give it so that these electrons would have the same amount of energy that the blue photon had. Okay, do you agree with that? Okay, so now instead of using it as an electron accelerator, we want to use it as an electron stopper. So here comes a blue photon, it gives all of its energy to the electron comes shooting out. And so if 2.8 volts was the right amount to accelerate it to that level, does it not make sense that 2.8 volts in reverse would be enough to stop it? Okay, so think about that. Okay, good, I'm glad to see that makes sense. Okay, all right, so then the question becomes then, is 2.8 volts going to be the right stopping potential in this case? Well, the thing is, we made an assumption about where we purposely ignored the work function, and we can't do that because in reality, every metal has a certain bond strength. So the electrons are being held, you know, they may be loosely, but they're still being held. Okay, so there is an amount of energy that does have to be overcome. So that means when these electrons come out, they are actually going to have slightly less energy, or maybe a lot less energy than the photon did. So it turns out that the voltage that we need to stop it will work out to be something less than 2.8. Okay, so let's do a problem like you might see in your homework tonight. Let's suppose that we bombard this metal with blue electrons and we change the voltage. Remember, we got a battery with a knob on it so we can change the voltage on it. And so when we do a bunch of experiments, let's suppose that our experiments show that the stopping voltage is 0.7. Okay, so it means anything less than 0.7 and some of these electrons are going to make it over to the other side. Anything more than 0.7, no electrons make it. Okay, so the stopping potential is 0.7 volts. So in your homework tonight, they're gonna say, okay, so we got blue photons, which we know how much energy they have. We've measured the stopping potential. Therefore, what is the work function for this particular metal? So remember, when we say what is the work function, what we mean is how much energy does it take to break the electron free? Okay, so this is a problem like you're going to see in the homework tonight. So let's see how we would do it. Well, we would say, okay, the energy of the photon, we calculated that a couple minutes ago, so we know what that is. And then we say, okay, so what we've got here is an electron gun in reverse, okay, where if our reverse electron gun, okay, 0.7 volts is enough to stop the electrons. So if we were to use it as a regular electron gun, okay, and the electron gun had a voltage of 0.7, then the amount of energy that those electrons have would be Q times V, which works out to be this 1.2 times 10 to the negative 19. Okay, so if this is the stopping potential, what that means is that this number right here, 1.2 times 10 to the negative 19, that is how much energy the electrons have. So now we can figure out what the work function is, because the work function is just going to be the difference, okay? Because the photon comes in with this much energy, okay? And this is how much energy the electrons have. So whatever is the difference between these two numbers, that is the work function. That's how much energy was required to break the electron free. So I don't think that tonight's homework is really going to be difficult if you understand what's happening. Now, if you're one of those people that just likes to say, well, just give me some formulas and I'll just blindly apply the formulas, that doesn't work here. You have to actually understand at a gut level what's happening. So I think that this way of explaining it that I did here, I think it will help you. One nice thing about recording the videos here is you can always go back and you can watch it a second time. And the book also does a pretty good job of explaining it too, but I like my way of explaining it. I think it's better than the way the book does. Okay, now there's one other thing we need to talk about. Well, actually, this here is just a summary of what we already talked about. So the incoming photon has this much energy. The work function is how much energy is needed to break it free, and then whatever is left over, that's how much the electron has. Okay. there's another thing that we need to talk about, otherwise you're going to have trouble with tonight's homework. Remember that graph that we used a couple minutes ago where the y-axis of the graph was not in joules? They used some other unit for energy. They used a unit that's called the electron volt. You need to understand that. So let's go into it and let's see. Okay, so let's say we got a blue photon, and so we want to know what the voltage is to give an electron the same amount of energy as the blue photon. So we figured out it was 2.8. I trust you're all good with that. Okay, so let's define a new unit for energy. And let's call this unit the electron volt, which we will abbreviate as EV. Okay, and so we're going to define it as the amount of energy that an electron would have when it's launched from a gun that's using a certain number of volts. So like in this case right here, our electron, which we purposely designed it so the electron would have 4.52 times 10 to the negative 19 joules, which is the energy of that blue photon. Okay, so this electron has that same amount of energy. So what we're going to do is we're going to define our new unit to say that the electron has 2.8 electron volts worth of energy. Okay, so 2.8 electron volts is equal to 4.52 times 10 to the negative 19 joules. Okay, all right. So if we measure our energy using electron volts instead of joules, it makes certain problems a lot easier. Okay, so what we're going to do then is we're going to redefine the energy of the photon in terms, instead of calling it joules, we're going to put it in electron volts. So we're going to say that this blue photon, we're going to say the energy of the blue photon, we're not going to say that it's 4.52 times 10 to the 19 anymore. We're now going to say that the blue photon has an energy of 2.8 electron volts. Okay, and so if we know that the stopping potential is 0.7 volts, then we want to know what is the work function. Well, if we are allowed to give the answer in electron volts, this problem becomes really simple. All we have to do is just take whatever is the difference between this. Okay, so whatever is 2.8 minus 0.7, so 2.1. So the work function in electron volts is going to be 2.1 eV. Okay, so in some of your problems tonight, they're going to ask you to work the problem in joules, and in other problems, they're going to ask you to work it in electron volts. And so you need to be very clear about when, how to change back and from one to the other. Okay, so the conversion factor to use here is that 1 electron volt is equal to 1.602 times 10 to the negative 19 joules. And hopefully you guys are going to say, hey, wait a minute, I recognize that number. That's the charge of an electron. Okay. All right. So in some of your problems, they're just going to say how many joules is equal to how many electron volts. So just use this number here as your unit conversion. It should come out straight. Pretty simple. Okay, so we're coming up on an hour. And as usual, I like to keep the online sessions down less than an hour. So I'm going to stop it here. Your homework tonight is chapter 27, problems 1 through 9. The problems will be very similar to the ones that we just went through. Please read the chapter before you do the problems. Okay, so Anna is asking about secret word. Yeah, where did I put my notebook where I write the secret word down? Okay. Oh, okay. All right. Jaren, I like that. Okay, so for the secret word for today, we will use what would have been our secret word last time, except I decided not to give a quiz. So za warudo. Okay, so that's going to be the secret word for today. Za warudo. Okay, good suggestion there. Okay, so that was a lot of pretty heavy stuff. I would not be surprised if a lot of you are sitting there saying, okay. So I highly recommend that you go through and watch this video a second time. I really think it'll make more sense the second time than it did the first time. And the book does a pretty good job of explaining it, but to be honest, I really like my way of explaining it better. I think it's a lot clearer. Okay, so are there any questions before I end the recording? Not seeing any questions popping up. Okay, so going once, going twice, sold.